interés. Gracias.
So, it's Yuri Bakthin, and he changed his title. Workers with...
So the point is that there are three talks, and they all will be on different topics. And so that's why this course is called Topics in Random Dynamics or something like that. But I figured out it would be easier for me and more interesting for you if I talk about three disconnected topics. So the first one has the biggest overlap with what the other lecturers, speakers are talking about. So today I'll talk about Burger's equation with random forcing and ergodic theory of the Burger's equation. And then the two next talks will be chalk talks, and there will be the second one will be about noisy heteroclinic networks, and the third one will be about systems with random switching. So they all are going to be, the connection between is really almost negligible. So there are some ergodic issues in all of these, but that's essentially the only connection. That these are all random dynamical systems, but of totally different kinds compared to each other. So today I'll be speaking about the Burger's equation with random forcing, or stochastic Burger's equation. Yes. Can you see this? So this is the plan of the talk. I'm going to start with some really basic reminders about ergodic theory of random dynamical systems, and I will go through some extremely simple example that has nothing to do, that is just a one-dimensional random dynamical system, unlike the main content of this lecture, which is about the stochastic PDE. And I will explain, using that example, I will explain what is the one force, one solution principle that plays the important role in all this business. And only then I will start talking about the Burger's equation itself, and so the history is mostly the Burger's equation in the compact setting, and then the main content of this, the more recent developments of last 5 years or so. So this is the progress on the non-compact case, and it started with zero viscosity, and they started with my joint work with Eric and Kostya here, and then I with my students I extended this to also positive viscosity, and so we'll see how far I can go. So apparently I have a whole hour and a half. We'll see how it plays out. So first, let us remind ourselves why we study ergodic theory. So this is all about understanding the long-term statistics of trajectories, and basically this is about consistency of averaging of measurements, right? So imagine, this is really vague, right? So suppose you just have some evolution in some space. So this process xt evolves in some space, and once in a while you measure that. So a measurement just simply means that you have a function that, given the state of the system, produces just a number, and then you want to make sense of this procedure of averaging. So does it make sense to take repeated measurements and take averages of them? And of course, if you have ever studied ergodic theory, then you know that these averages make sense if you have an invariant measure, if you have stationarity in this. But then still you can ask this question: is there a limit, and what does that limit depend on? And in principle, this limit can depend on the initial condition. And you can ask, how do statistical properties of the system depend on the initial condition? But if the limit exists and doesn't depend on the initial condition, the situation is called ergodic. I mean, this is maybe this is a slight abuse of the terminology, but this is more or less this is at least the level that I'm going to present all this in. So you can present this question what this limit depends upon as follows: what does the system remember in the long run about the initial condition? And of course, all this means that we are going to work with invariant distribution. We want to describe them for certain systems that we are interested in. So this is this super simple example of a linear random dynamical system. It is called ARMA, autoregressive moving average of order 1. And so this is a random evolution, and at each step, this is evolution in one dimension, right? So at each step, you take the current point x, you multiply it by a small number a, so things get compressed to 0, and then on top of that, you add the random perturbation that sort of pushes you away from the equilibrium. So had there been no noise, things would just have obviously converged exponentially fast to the equilibrium, but we have these noisy kicks that kick you out of the equilibrium. And say we assume that these noisy kicks are independent and have the same Gaussian distribution. So now suppose we want to study the system over long time intervals. It means that we want to take compositions of those maps, and this is what this composition looks like. So this is the iteration of those maps between times m and n. So you start with time. So you start at time m, and first you apply the transformation number m plus 1, then transformation m plus 2, and so on and so on. So every time it's a different transformation. So a is always the same, but the noisy inputs are IAD. And in this simple example, you can, of course, easily compute what the result of this is. And the result is this this expression. So what you have is this, these noisy inputs, they are all around the place, and each is multiplied by a squared, and so on and so on. And so the influence of this one in the long past is really small, right? Because this, if n minus m is a large number, then this is a very small number if a was less than 1. And so now you can ask, okay, what's going to happen to the dynamics over long-time intervals? I'm interested in long-term behavior. So the natural instinct, if you're asked about a long-time behavior of a dynamical system, is to start dynamics at time 0 or sometime m, and then see what happens in the forward time. But it turns out that, and you will see it immediately in this example, that it's much more useful, in a sense, and instructive to see what happens in the pullback limit. So the pullback limit is where, you do want to have this difference between m and n to grow, but instead you fix n, and you let m, the starting time, go to minus infinity. So what is the point of this? You sort of pretend that the infinity is now, the time infinity is now, and you want to understand what is the effect of the forcing in the past onto the present. So in a sense, you want to see what is worked out by this evolution, by this history of the forcing and the dynamics. What are compatible values at present time with all that history. And so so these are just words, but also, you see that in this example, this limit is extremely easy to compute, right? So so remember, n is fixed, and then m goes to infinity. But if you look at just as at the tail of this series, so every time you take m further into the past, you do not change the you just append one extra term essentially. And this extra term, it decays exponentially. And so as m goes to minus infinity, you append you add more and more terms that exponentially decay. And the result is that this pullback procedure, right? It's pullback because we are starting at more and more distant times back in the past. So the result of this is that this evolution operator from time m to time n, it converges to this operator from time minus infinity to time n. And the result is given just by this series. So it's a random variable that has index n, because this is the present time is n. Notice that it doesn't depend on x. So x is here, but the result of this procedure doesn't depend on x at all. So somehow it means that, from this ergodic point of view, and when I asked how does the long-term behavior of the system, how does it depend on the initial data? So here it turns out that it doesn't depend on the initial data. So this calculation shows that there is a serious loss of memory in the system. So this is the scheme of things. If you so this depends on n. You can do this for all n, and then the values of this process indexed by n, they are actually consistent with each other, right? This process xn, it actually satisfies this equation naturally, and you can just guess that this is true by the construction, but also you can just work with this random variable. You can multiply it by a, you can add the next xi, and you will obtain the same series just that ends with xi n plus 1. So this is self-consistent, which is nice. So the result is that you have this global solution. This equation is satisfied for all times from minus infinity to plus infinity. So it's a global solution that we obtain in this form. Secondly, this solution at time n, it is a functional of all the forcing in the past. So all these random influences in the past that is natural to call forcing or perturbation forcing. I'm thinking in terms of the stochastic PDE, where this will be really forcing. X of n is really almost surely a functional of the forcing in the past. In this case, this is just this formula, so it's obvious. Therefore, it is a stationary process, right? Because as inputs, you take this stationary process, and if you shift this by a certain time, then all these variables also will shift their indices, and so the result is that a factor of a stationary process is also a stationary process. Also, you can show that this is a unique global solution that is a stationary process. In principle, you can just take this equation and start with any point, and you can, if you want, you can go in both directions. This is a one-dimensional problem. There are no difficulties that are present in the PDE setting. You can go forwards and backwards. So you can go backwards, but the result is that you will have a global solution, right? You can define a solution that you can just invert this transformation all the time. But the result will be a solution that is not stationary. This one that we carefully chosen through this pullback procedure, it is a stationary. It is a global solution that is also a stationary solution, and it is a unique solution. It is a unique process with these properties. Okay. Right. So the picture is that you start. So this global solution, and you start at any point backwards in time, and then you see what is the effect on the present, and as the further you go backwards in time, the closer you are in the present to this ideal global solution. And also you can easily compute the distribution of this process at any time. I mean, all these are Gaussian, so you can compute that the result is also a Gaussian. And this distribution is a unique invariant measure for the Markov process. So in principle, there is this distinction, important distinction between the Markov process and the random dynamical system that generates it. So in the random dynamical system, I'm also watching these omegas, and in the Markov process, all I'm interested in is transition probability. So I'm going from time 0, say, to time 1, using the transition probability kernel, but I'm not really interested in how exactly these transitions are made. So the notion of Markov process is sort of coarse graining, and you forget some information about the random dynamical system. So all these properties together are described by this term, one force, one solution principle. And it's sort of self-explanatory, right? So to almost every realization of the forcing in the past, there corresponds uniquely defined, uniquely compatible point at present. So I'm talking about this for so long because this is, then we'll switch to PDEs, but this structure is what is really defining what goes on there.
The one source and the parameter is the letter A.
Huh? Pardon me?
The one force parameter is the letter A.
No, A is fixed. A is just what A is actually the deterministic part of the evolution, and by forcing I mean these random perturbations. So these noisy inputs that drive my system, right? So without driving the system, without pushing the system out away from equilibrium. Right. For different A, I will have different station distribution. I mean, this process is sort of in continuous time. This would have been Einstein-Uhlenbeck process. So you have contraction to 0 and noisy perturbations. So what the equilibrium that emerges in the limit is a combination of these two effects. This is sort of the dissipative effect where you get pushed towards the origin, and presence of the noise that pushes you around. Okay. So in principle, this one force, one solution principle, I mean, it's not that it's everywhere, right? I mean, I will speak about very interesting examples where it occurs, but this is a specific case of this more general situation where, in principle, you can have stationary processes that are generated by random dynamical systems, where at present there may be more than one value that is compatible with the history of the forcing. I mean, say if there is no forcing at all, but you have an attractor with non-trivial structure. So yes, there may be situations where we are almost surely any realization, almost every realization of the forcing in the past, at present it generates not just a delta function, not just one value, but a whole distribution. And so in general, it turns out that you can, I mean, this is a very general situation. In general, you can express invariant distributions for Markov processes generated by random dynamical systems by this averaging over pasts, and to each past, to each history of the forcing, there corresponds a distribution. This distribution is called the sample measure. So this is a generic situation. It's not hard actually to prove this theorem using some martingale convergence methods, but I'm not going to talk much about this. So I'm just showing this, but I'm going back to the one force, one solution, where all these sample measures are Dirac deltas. So there's uniquely defined present by the past. Okay, so now I'm ready to go into the Burger's equation. Many things are going to be sort of parallel to what Leander and Derek and Kostya, I guess, will say. But this is in the PDE setting where things are continuous in space-time or only in space. So there will be several variations on that. So this is the Burger's equation, named after Burgers, the Dutch physicist, who introduced it as a simplified model for turbulence. But what we will see is also it sort of shows that this is not a very good model for turbulence because it doesn't capture interesting instabilities in in Navier-Stokes, in real turbulence, in Euler equations. So there are lots of local instabilities and things are intermittent and so on. So in the Burger's equation that you see here, you do have this loss of memory situation. So things are much more stable. So from the point of view of turbulence, this is only a sort of playground, but it really doesn't capture many interesting things. But yes, I will explain how this model is related to fluid dynamics, and so all these are just various connections. So the reason why it is interesting to study Burger's equation is because it's connected to all kinds of interesting things. And I found it extremely stimulating to study the Burger's equation, and because it sort of stimulates you to read about all these. Okay, so I'm not talking about this. Instead, I'm going only to talk about mathematics. What does this equation describe? Throughout this talk, I'm talking only about 1D situation. You can talk about Burger's equation in multiple dimensions, but not in this talk. So U, this U, it describes the velocity, a velocity field. So you should imagine a real line that is filled with particles. At each point, at each time, there is a particle. The velocity of that particle at time t at point x is denoted by U of tx. And then there is this simple calculation that if you want to compute the acceleration of this particle, right? So imagine that U is the velocity, U of tx. And then there are all these particles moving around. So if you want to, so the first derivative of x is this velocity. The second derivative, that is the acceleration. You just apply the chain rule, and you end up with this, and you end up with this left-hand side. So this is one of the most basic calculations in fluid dynamics. So the result is that the left-hand side of this equation is the acceleration of the particle. So the right-hand side is supposed to give you all the forces that contribute to this acceleration. And in this model, it is assumed that there is external forcing F, and in the end, it's this external forcing F that's going to be random in the end. And also, if nu is positive, then there is also this Laplacian term here that is responsible for friction, and it's responsible for aligning velocities of nearby particles. And so there are two distinct situations here. If viscosity is 0, then this term is not present, and we will see in the next few slides that then it means that particles do not interact with each other, right? So this equation sort of says that the acceleration is only expressed in terms of the external field F. So they do not see each other until they bump into each other. And they do, and that's what the next slide will talk about. So in this case, there always will be shocks, discontinuities of the velocity profile that are due to particles bumping into each other, essentially. In the positive viscosity situation, this doesn't happen because this it smooths the velocity field enough so that it doesn't happen. So there is energy balance in this equation. So the energy is pumped in by the external forcing, and then it is dissipated either due to the Laplacian term here, or it is also dissipated in shocks. And so this is the same kind of balance that we saw in that linear system. So there is dissipation. I mean, if you leave the system to itself without perturbing it externally, then it will sort of relax. So there will be some relaxation to the equilibrium. But we do have this extra forcing, and it will be random. It will kick the system out of the equilibrium, and due to the presence of these two mechanisms, we are hoping that it is natural to expect stationary regime. So there's going to be certain balance between these two factors.
Question, just one minute. You is equal to 0, that means conservation energy?
Yes. Until particles start bumping to each other. Because so when solutions are smooth, so if you start with a smooth initial conditions, and with a smooth initial condition, then for a while, so these are so this is x, this is the velocity, right? So these particles have high velocity, these particles are slow. So for a while, maybe this is the graph. At the next moment, these particles move fast to the right and they retain their velocity. These particles also move to the right, retaining the velocity, but slower. And so there will be a point where these particles will overtake the particles in front of them. Until that point, the energy is conserved. But as soon as they start bumping into each other, if you're still interested in a univalued solution, I mean, if you pretend that these particles just ignore each other, then you will have this multivalued solution. And it is possible to study these multivalued solutions, but it turns out that from various physics kind of considerations, it makes sense to still work with univalued solution. And it turns out that the best way to do it, say if you want the average velocity to be preserved, is to cut it through so that these two areas, A and B, are equal to each other. But then, as you erase these two parts, the solution will have a discontinuity, right? It will be smooth here, it will be smooth there. And some of the energy will be dissipated because these particles that were here carrying some energy with them, you just remove them from the system. So this is sort of, I mean, you can see this as something artificial, but there is another point of view of looking at this, is that these particles that start bumping into each other, they form clumps. And when this clump is moving around, but then it is not seen by these clumps, they occupy 0 Lebesgue measure, and there are at most countably many of them. But anyway, so this is another graph that explains how we obtain a univalued solution out of a multivalued solution. There is no external acceleration. There is no the particles do not interact with each other, and their paths in space-time are straight lines, right? So it's just motion with constant velocity. So initial velocities are given, and then each particle just travels with constant velocity, and then at some point they start bumping into each other. And so the goal of these special solutions that I'm going to describe by variational principle in a minute is to replace all that mass there with a nice slit. So here a shock forms, this continuity of velocity, and it evolves. It is known, everything is known about how it evolves. The particles keep incoming and get absorbed into the shock, and in a sense, this is how the memory loss happens, because we do not distinguish about these particles after they are absorbed into the shock. So all this, this model can be called sticky dust, because these particles, they don't see each other, but then they bump into each other, they form a clump, and they stick to each other, they travel together. Okay, so I start with more precise description for positive viscosity. The reason is that there is this nice substitution that helps solving this problem. It's called the Hopf-Kohl transformation or substitution. So U is this, this unknown function that we're interested in, the evolution of velocity profile. It turns out that it's useful to introduce the primitive, the potential, and work with that. So this is the derivative of U, or capital U, with respect to x. And so you replace this small u with a new variable v. And then it turns out that this new variable v satisfies, after this logarithmic transformation, it satisfies a linear equation in v. V satisfies a linear equation. And this is the heat equation with multiplicative potential here. And these equations, they can be solved by Feynman-Katz formula, which should be known to all probabilists. And this is that formula. So what you have to do if you want to find the solution at time t at point x, then you sort of, from this point, you sort of emit a Brownian motion backwards in time, and then you integrate with respect to that winner measure. What do you integrate? You integrate the initial condition v at the landing point, right? So it took time t for this process to travel from this to 0, and also there is this exponential weight here. And what is this exponential weight aside from the constant? Here, this is the total potential accumulated by the path. And I'm showing this for so long because later, it will be really important, these things. Okay. So this gives you a well-defined solution of V, and then you can go backwards and reconstruct U. Suppose I'm interested in the zero viscosity limit. If you look at this formula and you're a probabilist, then you probably know that this looks like an instance of where large deviations could be useful. So this nu goes to 0, and you can just use the basic large deviation principle for the Brownian motion, multiplied by epsilon. Here it's multiplied by square root of 2 nu. So as nu goes to 0, you sort of apply this infinite dimensional Laplace's method, and you end up only with contributions from certain paths. So you can derive this from large deviation theory, but you can also derive this using PDE tools, of course. So as a result, you have to, in the limit, that integration in Feynman-Katz formula, it becomes this variational principle. So now to construct the solution capital U at point x, all you have to do is to consider all absolutely continuous paths, gamma, and for each path gamma, compute this action. This is called the action. And this is the potential action, and this is exactly what you saw in the exponential of the last slide. Now, what this is the rate functional in the large deviation principle for the Brownian motion. And also there is this contribution from the initial condition, and so this is just matched with the previous one. So you have this variational characterization of solution U, and it is natural to call the solutions that are obtained in this form the viscosity solutions. So this is now for viscosity equal to 0, but this is a result of viscosity of positive viscosity going to 0. So you have this solution. After you have computed the optimal values and the optimal paths, you have in fact, you have a foliation of the space-time into paths. So for each point here, you have an optimal path. And for some points, it turns out that you have two paths. And it turns out that these paths, you can identify them with particle trajectories. So initially, we don't know which particle arrives there, right? So we're given velocities of all particles in the beginning. We're given how they are accelerated here. So which particle arrives here? A priori, we don't know, but by solving this variational principle, we find the best path in this minimal action for the minimal action functional, and this path can be identified with the particle trajectory. So for most points, there is just one particle that arrives there, but for some points, there are two particles that land on this side at time t. Each one of them brings its own velocities, right? So this one brings a certain velocity from the left, this one brings a certain velocity from the right. And so it means that there is a discontinuity of velocities. So on the left, they will be more like this. On the right, they will be more like this. So one way to, after you have constructed these minimizers, you can construct the velocity field U in two ways. One is just differentiate capital U, because that's what we do here. Right? So capital U is the potential of this long. And another way is you have this interpretation of this path as the particle path. So you just have to find the velocity of this path. Velocity or slope, the slope of this path. The slope of this path. Okay. But you can hear me, right? Yeah. Can you? Yeah. Okay. So this is more for recording purposes, though? Okay. It's tempting to. Okay. Eric is going to sing for you. So in general, so this shock, they do not disappear. So once a shock is formed, it just travels around in space, and it always has, if it forms somewhere, then you can trace it for all later times. But they also, the shocks can collide. So they can move around, and it can happen that the two shocks merge, coalesce at some point, and so then they travel together from that point on. So in general, what you see is these hierarchical structures of shocks, trees, or I guess forests of shocks like that. Okay, so that was. There has not been any serious randomness so far, right? So there was randomness in the Brownian motion, in the Feynman-Katz formula, but it's not really. There it is. It's an auxiliary tool that was used to represent solutions. So now we are. This is the first time where we start studying random perturbations of the Burger's equation. So in this celebrated paper in the year of 2000, these four authors considered the Burger's equation stochastically forced on the circle. So all my pictures were on the line, but you can imagine that, you can have a circle, the circle, you can unfold it on the entire line, and you can say that you work with periodic forcing, or you can just say that you can really think about particles traveling on the circle if you want. And these particles are still accelerated by an external potential. So the potential that they considered was of this form. So you have several white noises, and each of them, white noises in time, and each of them was amplified by by a separate smooth function fj of x. So these are wide in time, and this is smooth. And so they had to make sense of this variational principle. You can do some integration by parts to work with this. So these details are not important for the present talk. One of their main conclusions is the description of the ergodic components and one force one solution principle on each of them. So it turns out that the Burger's equation preserves the average velocity. So if you start with some value of c on the circle, you will have the same value of c forever. And so it means that this is something that the solutions have to remember. So in the beginning of this talk, I asked this question: what do the long-term statistical properties depend upon? What do they remember from the initial condition? And so it's clear that they have to remember this because it's the first integral of the system. And in a sense, this theorem says that they don't remember anything else. So each of the random solutions remembers just this constant, the average value. But other than that, each of those sets forms an ergodic component. So on each of those ergodic components, there is a unique stationary distribution for the Markov process. If you start with some initial condition, over a long time you will converge to that distribution. But moreover, that distribution can be described in terms of a one force one solution principle that I will have to explain now. So the Burger's equation actually is invariant under shear transformations. So it means under Galilean transformation. So if I add velocity v to all particles, then the resulting flow of particles also solves the Burger's equation. It's just, in a sense, it's just shifting, changing the coordinates. You can switch to a moving coordinate system, and from that coordinate system, you will see that. You will also see a solution of the Burger's equation. It's just all the velocities are modified by the same number, by the same velocity v. And so in this picture, and many times throughout the talk, maybe I'll forget about various average velocities, v or c or whatever they are called. One should think mostly about the average velocity being equal to 0, because everything else follows from this case. So I'm restricting myself to zero average velocity. The space is the circle. The time goes upward in this picture. Suppose I want to do the pullback procedure. That means that I take any time t and I assign some initial condition in long distant past at time minus capital T. So this is capital T is very large. So this is long distant past. And then I solve, maybe let me just assign the initial condition that's identical 0, or anything else that just integrates to 0, the average velocities. And then I want to solve this equation from this time to this time. That amounts to constructing all these minimizers between these two times. And after I have constructed these minimizers, I can just look at the slopes, at the velocities of those minimizers at this time t, and that determines the velocity profile there. So the velocity at each of those points is exactly the slope of this minimizer. So this gives me the solution operator from time minus capital T to time small t here. The pullback procedure consists of taking this time minus t to minus infinity. And so it means that I take earlier and earlier times, I reconstruct the minimizers over longer and longer time horizons, and the fundamental theorem of that paper, it says that the finite right? Finite time horizon minimizers converge to some infinite, some one-sided infinite, semi-infinite, one-sided infinite trajectories. And they're also minimizers. They're infinite trajectories, so their action, the action of each of them is infinite. But still, any finite portion of them is a point-to-point minimizer. You cannot improve them locally. Using statistical mechanics language, so these one-sided minimizers can be seen as can be called ground states of this energy. So in terms of minimizers, we have this picture that minimizers, finite minimizers stabilize to infinite minimizers. By the way, this is very similar to what Leandro was explaining to you for discrete models. So he took a point, a distant point in a certain direction and pulled that to infinity, and he claimed that this path stabilized. So this is the same phenomenon. And right, these global these one-sided minimizers, now they're infinite, so they also define a solution, a velocity profile, a velocity field at time t. And since pre-limit minimizers converge to that, to these infinite minimizers, you can say that the solutions of the Burger's equation associated with finite time horizon, they also converge to the solutions, to the global solution determined by the infinite picture. And it turns out that this picture doesn't depend on which initial condition you take here, which can be explained, I guess, like this, that if you start with two different initial conditions, but they are in a long distant past, but you want an optimal action here, then what matters really what these paths accumulate from the environment, because you can have a contribution from the initial condition only, by so much, right? So you start with some initial, but you have almost infinite time to accumulate action from the environment, and so in the end that dominates over the initial conditions. So you have this loss of memory in this system. Okay. An important property is that these minimizers are hyperbolic. So it actually turns out that there is a global minimizer. There's exactly one minimizer that goes from minus infinity in time to plus infinity in time. And that minimizer can be seen as a hyperbolic trajectory of an associated Lagrangian, random Lagrangian dynamical system. Hyperbolicity means that in the forward time there is an expanding direction. Basically, hyperbolicity means that if you follow the system in the forward time, solutions, nearby solutions, they diverge exponentially fast. So here, the way to say it for those minimizers, for the minimizers in this picture, they converge exponentially fast to each other in the reverse time. And this is actually an important property because, so somewhere, somehow, okay, we're solving the Burger's equation, but also we simultaneously are solving the equation for capital U, the potential. And so if you remember, then to solve the equation for capital U, what do you have to do? So at any time, so you're solving from here to there. There is some initial potential here, and then to each path there's associated the action, and then the new potential here is the sum of the contribution, is the sum of the initial potential plus the optimal plus the action of this path. And again, this is very similar to the semi-group or something like that Leandro was explaining about his measures. He had measures plus path. This is the same kind of thing. So what matters is that the difference between two values of the potential here. And for potentials, it's really the differences of potential, the increments of potentials that matter. So the difference between potential here and here can be computed as follows. You take this path, the action of this path, plus the increment of the action here, and minus the action of this path. Okay, so now the time is infinite, and you sort of you want to compare actions of two infinite paths, and you can do this because this distance between them becomes exponentially small, and in the end, as the time horizon increases, as you add more and more discrepancy to those paths, you add exponentially decaying discrepancies, and so in the end, you can make sense of the action of this infinite path minus the action of this infinite path. And this difference is called the Boozman function. So in the original paper of Hani and Mazel Sinai, so they were not called Boozman functions. But in essence, this construction and this understanding was there. And so Boozman functions in the context of percolation, it was introduced by Hoffman, I guess, right, in like 2005 or something like that. So Boozman functions, so that's the notion coming from geometry. Huh? Newman?
Yeah.
Okay. Okay.
You don't have necessary coalescence here.
Pardon me?
You don't necessarily have coalescence here.
So here I don't have coalescence. That's actually a very good point. So in fact, these minimizers, they solve the Euler Lagrange equation. So the second derivative is given by the forcing, and so of course the forcing is white here, so you have to explain what that means. But essentially, if you have a second order ODE, then the entire trajectory is determined by you take any time, and at that time you specify the position and the first derivative, and therefore, if they had they coalesced over some time interval, they would have been the same trajectories forever, just due to the uniqueness in the ODEs. So they cannot coalesce. So this is the difference between this and discrete models. But hyperbolicity is the best replacement for coalescence. Yes. So how do you obtain, at least how do you hope that why do you hope that there are minimizers, that there are global minimizers, or that this picture has a chance of the finite time minimizers might converge to something? Well, it turns out that there are bounds on velocity of minimizers. So remember, there was this term, the kinetic action term. Imagine that you have a very fast path, so it has a very large velocity. If initially the velocity is very large, then this path makes a circle around the circle. It comes back, and what it accumulates is, so the increments in x squared divided by the increment in t. So this is a simple calculation, right? The velocity. Imagine that the velocity is just constant, right? So then velocity is v, and the time it takes you is t, but velocity is equal to delta t. Velocity is delta x over delta t. So this results in this formula. So over short time intervals, if the displacement is of order of 1 and delta t is small, then this is a very large number. So by doing this, you accumulate a lot of action. And a path like this it's much better, because you don't accumulate any. I mean, you do accumulate some random contributions from here and along this path, but you can make this into rigorous mathematics and convert this into the fact that the velocity of the minimizer over any given time interval between time 0 and t0 and t1, the velocity is bounded by a random constant. And so if there are some minimizers passing through this region, their velocities just have to be bound by that random number. And now if velocities are bounded, then you can use compactness, you can take subsequences, and at least that's how you construct minimizers. And so uniqueness and hyperbolicity, so these are other sophisticated issues, but at least from this picture it should be clear that there is a hope to have. Is that the question?
Yeah. If we don't have non-conservation system, we still have the
Velocities are well. It's not that they're uniformly bounded in time. Well, the noise can accelerate these particles seriously locally. So there are fluctuations, and rarely they become large. So they behave as a stationary process. So what is the question again?
We still have the velocity bounded, even if we don't have a potential right field symmetry.
I'm not sure I quite understand. I mean, essentially, if you have any slight modification of this, the fact that you will have bounded velocities it's a very well on any finite time interval bounded by a random constant. This is a very general statement. I mean, here I'm using the quadratic nature of the potential of the Lagrangian, but it is true for a broad class of Lagrangians or Hamiltonians and a broad class of forcings. So I'm not sure if that answers your question, but I'm trying. Huh? So honestly, in this talk, I'm not considering anything else but quadratic Hamiltonian and quadratic Lagrangian. In general, it is possible to consider these systems. On the circle, everything is understood. And I will mention these works by people who are present here. Now, in the non-compact case, that is the main subject of this talk. I told you. It's difficult, and I will explain why. Okay, but now let's move forward. So this is the, I guess, incomplete list of results that are related. Things have been understood on the torus, on a bounded interval. There are simplified proofs of hyperbolicity in one and multiple dimensions on the torus. There is a recent paper by Hyre and Mattingly about strong Federal property, which also implies ergodicity for the KPZ equation, which is just the Burger's equation with space-time white noise, essentially. But it doesn't explore that paper doesn't explore the contractive nature of this dynamics. It uses something else, the regularity structures, whatever. There are PDE papers. PDE means that, like, not variational methods, but using some test functions, kinetic solutions, whatever. And there is a direction. There is a school of thought that calls one force, one solution principle synchronization by noise, And they didn't consider this kind of equation, but morally their ideas sort of apply to this setting. Now, in the non-compact setting, there is nothing like this. So in the non-compact setting, a priori, as you increase the time horizon, the paths potentially can become totally wild. And so if you want to extend this program to the non-compact setting, you have to explain why the paths over long time intervals, why long minimizers do not become wild. So there must be some tameness. And so there were some papers where various people tried to deal first with quasi-compact setting, where first you're still on the entire real line, but most of the forcing happens in the middle. So you sort of stir the particles in the middle, and then you see what is the effect of that on the entire space. Now, but the real thing is these papers where we considered truly space-time stationary forcing, and the solutions do not have to decay at infinity or anything. So the solutions have to be stationary processes in themselves. And so these two models are based on two different. These two papers are based on two different models. In one of them you have coalescence. In the other one you don't have coalescence. So this is more like a true Burgers equation. So let me explain what these two models where this ergodic program goes through are. So the first of these models is based on Poissonian forcing. So Eric, are you going to talk about Poisson things?
Yes,
Okay, so it must be similar to somewhat similar to what Eric is going to talk about, and there is a reason, because this is how we met. Eric was talking about his work with Leandre, and at that time I started thinking again about the Burgers equation, and it turns out that the structure of this variational problem is actually very similar. So there are difficulties, but a large part of this problem is very much inspired by the previous work by Eric and Leandre. So we assumed here that the forcing is concentrated at Poissonian points. So in space-time, consider the space-time homogeneous Poisson process. And each of those Poissonian points has action contributes action -1. And all these paths that I want to consider, they're supposed to minimize this action where the potential action is replaced by just minus the number of Poissonian points visited by the path. So you have a minus here because if a point carries a positive weight, you can just ignore that. Ignore that point. It's not useful for anything to try to get to that point. And so somehow this becomes the intrigue of this is the following. So I want to accumulate many Poisson points by a path, but I cannot take all of them because there is this penalization by the kinetic energy. And so this is a little harder than the questions of like last passage percolations where the paths are upright, but and the difficulty here is that these paths can have arbitrarily large velocities a priori. In the upright path, if you look in the rotated coordinates, so this is a Lipschitz one trajectory. So the slopes so this is, in a sense, this is a hardcore constraint. You can only move. You're always supposed to move in this corner. In the Burgers equation, a priori, you don't move in any corner, so you have to explain why the optimal paths still behave not too poorly. So the other model that I considered, it is so unlike the previous model, where we will see that there is coalescence. In this model, there's no coalescence, and that's why it's in a sense, it's harder and more interesting. So this is a model of discrete forcing. So the kick forcing is applied at every integer time. So at every integer time, you change the velocities of all particles on the entire line simultaneously by macroscopic increment that is given by stochastic process. And then between time, say 0 and 1, you solve the unforced Burger's equation. Then at time 1, you apply a new kick, and then you solve unforced, and then kick and unforced. And so you also get
in your picture, you didn't draw any shocks. The shocks will appear.
Well, this is right. So the shocks actually start emerging. Say this, say shock. You already have here a shock. In reality, this entire picture is also foliated by minimizers, and the shock propagates up to there. And so in reality, this is all foliated by trajectories, and there is a well-defined trajectory of this shock between those times. The shock is not straight line. No. It's slightly curved. Slightly. Right, so there is also this action, right? So there is initial condition, kinetic action, which is now discrete potential action. And so these are just, those papers on last passage percolation that are relevant for this program. Of course, there are many others that I'm ignoring in this story. Many things go back to Chuck Newman. Okay, summary of results. It turns out that the results are precisely more or less the same as in the compact setting. It's just the techniques that we have to use are much harder. So essentially, the situation is the same. So for each average value of velocity, there is a global solution with that average value. That global solution can be obtained via a one force, one solution principle. That is, it's uniquely defined by the history of the forcing. Right. So again, you have this sort of foliation into those ergodic components. For each fixed v, there is a unique invariant measure for this Markov process that is given by these formulas, and this the way you can represent that invariant distribution for the Markov process is via these delta measures, right? So to each history of the forcing in the past, almost surely you can associate a unique velocity profile at time 0, say time 0, with prescribed average velocity. So you can understand this global solution as a one-point pullback attractor. In terms of minimizers, I mean, of course, all this story is about minimizers. The theorem on the previous slide was the result for the solutions of the Burger's equation, or the associated maybe Hamilton-Jacobi equation. You can reframe it like that. But in terms of minimizers, this is what you have. For every point xt, there is a one-sided minimizer with prescribed slope. It turns out that all these minimizers coalesce for this picture. All minimizers with the same slope coalesce with probability 1. And right, so they meet at some Poissonian point, and then they go together. So that's similar to the discrete models that we already have seen. This will be the same in Eric's talk, I guess. And this is due to this strange, artificial nature of this model. So I introduced this forcing specifically to make last passage percolation tools to work, along with the shear invariance. That's also useful. In the kick forcing case, this picture cannot possibly be true due to that Euler equation Lagrange equation kind of argument, right? If two minimizers go together, at least a little bit, then they totally coincide, so they cannot coalesce. And it is sort of a shame, but the best statement that I can prove at this point is not hyperbolicity, which we believe holds. What I can prove is a much weaker statement where exponential convergence is replaced by just polynomially decaying function, right? I mean, I'm comparing the difference between the two minimizers to the inverse of time. So this is supposed to be exponential, in fact, but I'm not proving that. And also, this is just a limit statement, which means that it's not a true limit, but only at times these trajectories get close. How close they get, this is how. But still, it turns out that this much weaker statement than the truth that we believe still this allows to define the Boozman functions along subsequences. So we have these places where these trajectories they get close to each other, and so now you can compare actions, say of this part and this part together. And it turns out that it is sufficient. This turns out to be sufficient, and the entire ergodic program goes through in this case as well. So the way the technique works, so there is, certain things here are about subadditivity. So this is the theme that everybody will say something about subadditivity in this. So if you consider just this action, so there's no initial condition here, right? So they're just kinetic and potential, and you can consider the best path between 2 points, between this and that one. And then if you take 3 points on the same line, then the action, if you combine these two actions, maybe the combination of these two paths is not optimal. So this may be better than the other two. Therefore, you have subadditivity, and due to subadditivity, you can apply subadditive ergodic theorem, and you can claim the existence of the shape function. Proving this is actually, it was a story, but it can be done. So the nice thing about this Burgers model is that the shape function that you obtain here, it is actually, we know it up to a constant, up to an additive constant. So there is this symmetry in the model that is the Galilean shear invariance. You can switch to moving coordinate systems, and just by these transformations of space-time, you can compute precisely that the shape function at point V is V squared over 2 plus a constant. And it's nice to have this to have a strictly convex shape function. And the quadratic function is the nicest convex function you can imagine.
Simple, nice.
It is crucial. It is crucial to have curvature bounded below. And so we have linear growth, okay, and also there is this concentration inequality that says by how much the optimal action essential, right? Complexity means that going straight is better than going than taking averages of the shape function with different slopes. So we see how can we prove the existence of minimizers of one-sided minimizers? This argument doesn't work. But straightness provides replacement for take long minimizers, and if they deviate too much, then we have a violation of straightness. So it means that we have to pass through certain regions, and then the Poissonian forcing set, we see that there are only so many Poissonian points in there, and you can choose us. There are not so many points there, so many paths have to pass through the same points and choose some sequences. So it goes. The same picture that the author showed, it's a zoom out. It was done by summer. It's a summer project of the undergraduate.
Could I go back to one more? This one. So you talk about some points now in binary end, and you substitute that. I can understand that. What happens in the flip force?
Well, it's even easier.
This is line.
Yeah, but you can it's just compactness, so they're restricted to certain intervals.
And therefore
you can choose if it's a bounded interval, choose convergence extents. Okay, so these are just the names of people who have been doing sort of similar things in the discrete models. Right, so I still have, 10 minutes?
yeah.
10 minutes, and so in these 10 minutes I will rush through the positive viscosity case. So that's the most recent work that I've been doing with my PhD student Yuri. So there are papers that have studied the situation in the compact case, positive viscosity in compact case. The only paper in the non-compact situation is Kiefer's paper that's written for high dimensions and small forcing. Somehow it is a different kind of sports where you can write down global solutions as just series in the spirit of perturbation theory. So let us look at the one-dimensional Groundspace equation on the entire real line. So this slide reminds us that we have Feynman-Cutts formula, Hopf-Cole transformation, Feynman-Cutts formula. If we look at this formula, we see that what we get here is a cycle of random linear operators. Right? So you start with, so this is the function that you're applying the evolution operator to, but the evolution operator is a linear operator. So it is like multiplying a vector by a random matrix, except this happens in infinite dimension, in a seriously infinite dimensional situation. So you also have this situation where you to go from time 0 to time t2, you can first go to time t1, from time t1 to t2, and that amounts to using the position of these operators. So it means that you have product of infinite dimensional random matrices that are sort of renewed all the time from time to go. So what we are after here is a version of Courant-Frobenius theorem in a situation with localization. The first theorem of this sort was obtained in our paper in the paper of Kosti and myself. But this is the situation that we are really after. There's no localization of any sort. So things are going, the forcing happens
So it turns out that although this is a useful way of thinking about this model, the details are they do not follow from there in any case. Okay, so Cake-Burgers equation with positive viscosity. Right, so I already explained what cake means. So we apply forcing only at integer times, and then we solve the unforced Burgers equation between those integer times. So the final Gauss evolution operator now it is indexed by integer times, and therefore we have this Gaussian products of Gaussian densities there, and this partition function helps us to represent the evolution operator. So this is really just the Feynman-Cast formula in the time discrete setting. So the basic object here is a random walk, it is Gaussian. On top of that, there are these exponential weights that are accumulated by the graph. So in a sense, what you see here is an integral of the initial condition of the with respect to a Gaussian random walk that is reweighed by these exponential weights. So it means that it is natural to look at this problem from the point of view of polymers. So polymers is a whole direct polymers is a whole field that is in a sense parallel to mass passage propagation and stuff like that. So where instead of finding an optimal path, in the random environment, you consider a random distribution on paths that is given by the Gibbs measure. So this is exactly that situation. You have this Gibbs measure. The free measure is the Gaussian random walk, and it's reweighed by exponential weights that come from the potential. So this picture describes. This is an attempt to draw a random direct polymer between 2 points, and as a part of the zero viscosity program, we proved that if you take 2 points and find the optimal path between them and take this point to infinity, we would have an infinite one-sided minimizer. So the question here is, if you take this point to infinity and keep reconstructing these random polymer distributions, what will you get? And it turns out that this can be done, and as the point goes to infinity, we can obtain what is called the thermodynamic limit for those Gibbs distribution, also known as the infinite volume limit. And it turns out that for each fixed slope, there is a limiting, and for each point here, there is a limiting infinite volume limit. It satisfies the Gaussian condition, so it is unique in some sense, and this limiting measure on those infinite paths, it is concentrated on paths with this slope v. And so instead of the one-sided minimizer, now we have this object that is an infinite one-sided polymer measure. That makes sense only as it's a measure on this path, and every restriction on an infinite interval is a regular polymer point-to-line polymer measure. So this is the first theorem of this kind, except an exactly solvable log gamma polymer case by Zimmer and friends. Right. So the techniques are harder because instead of the straightness statements becomes something like this. So you have to show that these paths receive a non-small weight only with very small probability. So this is precise statement. So you have to unfortunately work hard. So stationary solutions of the Burgers equation can be obtained just by you construct this measure. Now you go backwards in time, construct this thermodynamic limit, and then it turns out that if you want the solution of the Burgers equation, the global solution, you just have to take this polar measure and integrate x minus y with respect to the marginal distribution here. And so this is the theorem of the Dynamical. It says that such, in fact, these functions that they can be obtained in such a way from polar measures, they are global solutions of the Groundspace equation. That's the unique global solution with the specified slope v. You have one Boltzmann solution. You have this entire thing. And just the last thing that I have to say is that the most recent result here is the convergence of the directed polymer measures to one-sided minimizers. Right? So I mean, up to this point, I have constructed one-sided minimizers, so that's time goes to infinity limit, and I also constructed thermodynamic limits for polymers, so that's also time goes to infinity limit. On any finite time and time interval, viscosity goes to zero, so that's that large deviation principle that I talked about. Okay, but why do these limits commute? So can I interchange the order of limits as viscosity goes to zero? These infinite objects, do they converge with each other? It turns out they do. This is our most recent work, and it has, as everything in this program, it has two phases. One is that so polymers converge to one-sided minimizers. The other is that the global solutions of the Groundspace equation converge to with positive viscosity converge to global solutions of the Groundspace equation with zero viscosity. And invariant measures converge and all that. So again, this is the reference to the related work by the group. I like to give a list of problems that are open and that are related to this. And this is my last slide. So of course it would be interesting to obtain many of those things for the general Hamiltonian, but for the general Hamiltonian we don't know the properties of shape function well enough. Essentially that's the situation. It would be nice to, what's happening in higher dimensions, you can say something, but not so much. Do these things exhibit true KPZ universality features? Probably, they're supposed to, but there are no results. What about statistics for shocks and concentration of minimizers, right? So minimizers tend to concentrate, but I have given you a very lousy description of what they do compared to what we think they do. And so actually there is a paper of Kostya and myself that is going to be published in Linearity, where some of these issues are addressed as conjectures. And that's, I think, the weirdest paper that I've contributed to, because it's interesting, but there are a lot of conjectures. Okay, so I should stop here. Thank you very much.
Any questions or comments?
Yes. So when you look at the shock, at this kick force in so there was, I guess there was an advantage in the polymer case where you would have this, where you discretize somehow this kind of fudge, kind of final touch form.
Yes.
Does it also mean that it's unclear what you would have to do in the Poisson case?
Well, I certainly believe that the same program goes through in the Poisson case, and it's just, writing another paper about the same stuff. You don't think there will be any difficulties? No, there shouldn't be. I mean, there will be technical things to overcome, but essentially, it shouldn't be too difficult. I think you should basically, because the Poissonian model, actually we discussed it once. Remember in Bielefeld?
Comment.
Yes. So since then, comments and then we wrote some draft about that model, the different aspects of that. It's not a paper yet. It's something weird, but. Yes, this program should definitely go through for that complex program. I mean, I guess the biggest difficulty is to not even just to define the model, right? So that model is a distributions. You have these polymers. So this distribution of paths that go, through this cloud of Bosnian points. And so it's composed of Brownian bridges between these points, and you can see what they do between points. So you can solve a heat equation with the multiplicative forcing that is given by these Bosnian points. You can write a series representation for that if you want. So you can do things.
These things sound more difficult than what you could do here.
It seems to me that this is not hard. I'm certainly not writing that paper because it's going to be it's going to be more or less. I don't think that there will be any new ideas there.
Another thing I was wondering is you prove this convergence of the infinite volume measure to the actual minimizer.
Yes.
So in what sense would that be? How strong is that convergence? You could prove.
Well, I mean, so the actual statement of that theorem it requires some caution. So these the polymer measures. So it says
So I guess you couple the forcing somehow?
yes, the forcing is the same.
Yeah.
And so these on any finite time interval, the finite dimensional distributions of the polymer measure converge to the delta measure on the minimizer. And since this is discrete time setting, so that's equivalent to weak convergence on for all times.
Because in between it's obvious what happens.
You don't look at it, right? So you only look at
The show.
right at the shot. At the kicks. You only look at the integer times. And so the convergence actually holds true only for non-shock points, right? So because at the shock there are two infinite minimizers, so potentially there are two candidates for the limit. So this limiting measure, I mean, we don't know if it concentrates on some mixture that may depend on time. I don't know if it stabilizes really. But there is, so in 1D there's this additional feature that you have on atonicity. So these particles, so say for the implicit case, say this is point X, right? And this is point Y that ended up here. And so what is the velocity between them? So the velocity assigned to point X, u of X minus X minus u of X is equal to Y, because this term is equal to 1, so the particle moves with constant velocity, and this point Y depends on X in monotone way. So this function X minus u of X is a monotone function. And the topology that we prove the convergence is sort of borrowed from the world of monotonicity. If you have monotone functions, then you can introduce a topology that is similar to convergence of distribution functions, right? So distribution functions,
The jumps don't they?
right. So you ignore the jumps. You say that you require convergence for weak convergence of one-dimensional distributions. As we all know, it is sufficient to require convergence of the distribution functions at all continuity points. So we define the analog of that topology here, and that's what we prove. So it turns out that this quantity also depends on X in a monotone way. So you can, x minus that velocity, that is the integral of u with respect to the marginal measure. So that also so there is that monotonicity. You can prove convergence of these monotone functions to each other only at continuity points, and that's already a very strong convergence.
Cool.
Thank you.
Any other questions? Well, I have another one, but I think I will wait because we are a little bit tight. I don't know what were thinking the organizers when they made this schedule. And so, thank you again. So we can have 5 minutes. So,
Yeah, even if